Hi guys, so in this video we're going to talk about 4 or 5 questions from revision paper 4. These are questions that I have selected and I feel that they are rather difficult. And to solve these questions that I consider hard, there's always a little gimmick at the end of the question that you actually have to find. So let's not talk so much, let's start off with the first question. Here we have question 3, the vectors question. This is a purely algebra question. You don't have to visualize any lines, you don't have to visualize any planes. Refer to origin O, A and B is such that OA is A, OB is B, point C is on OA, such that the ratio of OC to OA is 1:3. So you have OA, line passes through AB is given that angle BOA is 60, A, modulus A is 3 modulus B. This means that the length of A is 3 times the length of B and it forms 60 degrees. So sort of like this. This is point B. This is point A, and this is 60 degrees. You have a line passing through AB. So this is L. By considering B minus A dot B minus A, express B minus A modulus in the form of K modulus B. So B minus A dot B minus A, you don't really have to refer to the graph at all, but do know that we are actually talking about this factor here. So this, according to dot product, it will give you mod B minus A whole thing square, because A dot A is mod A square. B dot B is mod B square. Now I'm going to expand this bracket using normal algebra. I'll get B dot B minus 2 A dot B plus A dot A. It doesn't matter whether it's B dot A or A dot B, they mean the same thing. It's commutative. And this would be this. And then this is just mod B square. This is 2 mod A mod B cosine of the angle between A and B, 60 degrees, which turns out to be half. So later this half is going to cancel with the 2. And then I have A dot A, which is mod A square. All good? Mod B square, I'll leave it because they want it in terms of mod B. A can be written as 3 mod B. So I'm going to change everything. This 2 is going to cancel off with cosine 60. So I'll have 3 mod B square. And then we have mod A square. Since mod A is 3 mod B, mod A holding square will be 9 mod B holding square. This will be. How many do we have on the left hand side? 9 plus 110, 10 minus 3, 7 mod B square is equals to B minus A holding square. If we want to find out what is B minus A, it is simply root 7 mod B. And there we have it, the first part. Nothing very special. You don't even have to refer to the diagram other than maybe use this 60 degrees. We can just do it without even drawing this. Now next question, find in terms of B the shortest distance from C to L. So C, I'm going to bring in C. C is actually on OA such that it's 1:3. So we have C 1/3 along the way. This means that if C is here, the ratio of this length to this length is 1:2. And then we are going to create the shortest distance to L, which is 90 degrees. And take note, this is the height of projection of CA onto line L. To find the height of projection, we're not finding length of projection, we're finding height of projection. Height of projection will be AC cross the direction vector of the green line L, hat. So the direction vector of green line L, we actually found it. It is B minus A. The hat of this would be B minus A whole thing hat. So I'm going to take this picture and shift it to a blank canvas. So now we know that the height of projection is just this expression alone. Let's go and find out what this expression is, because once we find this expression, when we mod it, we will find the height of projection. So it's a huge handful. It is Mod AC cross B minus A whole thing hat. AC will be C minus A. Cross B minus A hat is B minus A over mod B minus A. Luckily for us, we have found this in the previous part, but I'm going to sub in the final few steps. So this is the answer already. We just have to evaluate it. What is C minus A? C minus A, C is actually just 1/3 of A, am I right? C to A, 1:3. Therefore, this can be written as negative 2/3 A cross B minus A over mod B minus A. What is this numerator? Let's find that out. I'll get negative 2/3 A cross B plus 2/3 A cross A. What is A cross A? A cross A is actually just 0 because they are parallel. So this is gone. This leaves us with 2/3 A cross B over mod B minus A. What is A cross B? A cross B is mod A, mod B sine 60 degrees divided by mod B minus A. Mod A is 3B. So the 3 is going to cancel off with this 3. The B is going to combine with this B to give you 2 mod B square. Sine 60 is root 3 over 2 divided by B minus A is, as previously we found, root 7 mod B. Root 7 mod B. Clean this up, we will get root 3 mod B over root 7. Rewrite this as root 3 over 7 mod B. And there we go. That's our answer. That's the height of projection. The shortest distance from C to the green line. All right, next up, we have this disgusting looking question full of square roots. And we can't really do much to the square root because it's stuck with a plus sign in the middle. Not much we can simplify. You see all this ugly looking square roots. But you just have to be brave and persevere through all this algebraic manipulation. The hard part is actually the last one, but everything leading up to it is not, say, very easy as well. So let's take a look at the first one. Prove that this fraction is equals to this difference in two square roots. One look, we know we should rationalize it. So let's see, 2n plus 1 root n squared plus 2n plus root n squared minus 1. If we rationalize it, we should rationalize it with conjugate of the denominator, root n squared plus 2n minus everything else the same. What this will give us at the bottom would be the difference of a squared and b squared. Simply n squared plus 2n minus away n squared minus 1. Above we will get 2n plus 1. And of course I'm not going to expand it. I'm just going to leave it as it is. Even if we expand, we also don't get anything nice. So why expand, right? Let's see what we get at the denominator. Denominator, we will get n squared minus n squared, which is 0. And we have 2n plus 1. Aha. Luckily, we didn't expand because that 2n plus 1 and the denominator will just cancel off nicely with this 2n plus 1, which leave you with just n squared plus 2n minus root n squared minus 1, which is what they want you to show. 2 marks. Done. Second one, hence find the summation of this. It's very obvious that we have to use method of difference here because we have already expressed this, which is this, as a difference of two expressions. First step, we don't even want to copy this because I know this is just this. So it's just root n squared plus 2n minus root n squared minus 1. Sum from n equals to 1 to capital N. So here the moving part is n. These are the moving parts, 1, 2, and 3. So method of difference, all you need to do is list out all the terms. When n is 1, this would give us root 3 minus 0. Second item, we will plus when n equals to 2 now. 2 square 4, 4 plus 4, 8, root 8, 4 square minus 1 minus root 3. Aha, you sort of see it here. Let's do a few more just to solidify our number pattern. And then when n is 3, this is 3 square, 9, 9 plus 6, 15. Here I'll get 3 square minus 1 minus root 8. So it is now clear that the cancellation goes this way, this way, this way, so on, so on, so on. And if we were to continue doing this, we have 4 terms at the end. This will be cancelled off with this will be cancelled off with the third last term. So what survives is this one here and this one here. This term here, this one in green, is actually when n is equals to capital N, the final term of the left term. Root capital N square plus 2 capital N. Simplify, because this is just 0, you will get just n square plus 2n. And we're done with the second part, 3 marks. Third part now, which is just part A, deduce the value of n equals to 2 to n of this slightly different expression. Now let's compare this with this. We notice there are a couple of changes. Mainly here becomes a minus, and then the insides became slightly different, and this remains the same. So every time they ask you to do a deduce of something that looks similar, always start off by copying what you see, which is what the question wants. And then we will use the substitution method. We will substitute what we know with something such that it looks exactly like what we already found out in the previous part here. We know that this is root n squared plus 2n. So let's go ahead. What values of n do I want to replace it by such that this red color one will look like this green color one? You have to sort of guess a bit. But after a while, you should realize that if I replace n by r plus 1, the numerator will become 2r plus 1 minus 1, which is 2r plus 2 minus 1, 2r plus 1. It looks like the numerator here. Just that I changed the alphabet from n to r. So then what about the denominator? Would this work for the denominator? It has to work universally in order for you to say that this is an okay substitution. So it works for the top. Let's try it at the bottom. The first term on the bottom, we get square root n squared minus 2n. We replace it by r plus 1, we'll get r plus 1 squared minus 2, r plus 1. This gives us r squared plus 2r plus 1 minus 2r minus 2. 2r minus 2r, 1, negative 1, we will get r squared minus 1, which coincidentally is the bracket in our previous expression. Third item, see whether it works. Final item, n squared minus 1. If we replace the n by r plus 1, we will get this. Expand this, I will get r squared plus 2r plus 1 minus 1, which gives us 0, which is simply r squared plus 2r. It really looks like the previous one. So if it matches here, here, and here, we say that this substitution is correct. So we can go ahead and substitute n by r plus 1 into our new expression here. This will land us with this. I'm not going to write the boundaries first. The content will give us 2r plus 1 root r squared plus 2r plus r squared minus 1. Everything the same as our green expression. What about here, the boundaries? Previously is n equals to 2. I replace n by r plus 1. This will become r plus 1 equals to 2. Bring that 1 across, I will get r equals to 1. Above, we want to go up to n equals to capital N. So now you have substituted n away by r plus 1. So where do we want to get to? We bring the 1 across, we'll get r equals to n minus 1. So this means that we want to find out until n minus 1. So the difference between this new red version after substitution, we haven't changed anything yet. We just replace the n with r. We haven't actually changed the grand total. We're just writing it in another equivalent form. So we know that in the green one, the previous part, if we sum to n, we will get this expression. The only difference now is we want to sum from 1. Instead of going to n, we only reach n minus 1. This means that the answer to this is my previous answer, and instead of writing n every time, I replace it by n minus 1 because that's our destination. If our destination is capital N, this will be capital N square. If our destination is n minus 1, our destination is n minus 1 square plus 2n minus 1. Let's simplify this. Expand this bracket. I'll get n squared minus 2n plus 1 plus 2n minus 2 n squared. This is gone, so n squared minus 1 is my final answer. Final part, which is a real weird one. Summation of 2n plus 1 divided by 2n minus 1 is greater than root n squared plus 2n. We have seen this in our previous answer because that's the answer to this part. N squared plus 2n. Now, if you take a look at this, you might think that, oh, maybe I see a 2n plus 1 here. I see another 2n minus 1 here. So this means that I have to combine these two answers to sort of stack them up to get me this, and then somehow prove that it's greater than this. Well, that might work if the denominator is the same. However, this time around, denominator is not the same. You don't really have a good way to combine this answer and this answer. So the correct way to solve this is make use of this idea of inequality. Since we know that summation of 2n plus 1 over this square root gives us root n plus n squared plus 2n, right? Let's contrast this with part B, this expression, root 2n plus 1 over 2n minus 1. The only difference is the denominator here versus this pink one. And you ask yourself, if they want you to show that this is indeed greater than this, which is this, they want you to show that the green one is greater than this gray color expression here. This means that the pink color numerator is actually smaller than this. Once again, if the gray one is this expression and you have this blue denominator, this must mean that in order for you to show this one is greater than this, the denominator has to be smaller. So this is what they want you to show. To show this is true. We want to show that this sum of two square roots is actually greater than 2n minus 1. So as long as we have a way to do that, you'll be fine. The correct way to do this is actually weird. It is to factorize out the inside. N, we will get n plus 2, right? Do you agree with me that this is greater than n times n, since you have a plus 2 inside? And n is always positive, since n always goes from 1 onwards. This is true. This can be also expressed as this. This is greater than n squared, right? This means that it's greater than n. So this is part 1 of my proof. Part 2 of my proof, I will need to take a look at the second half of this expression, n squared minus 1. If we were to factorize it, we can write it as this, n plus 1, n minus 1. Do you agree that n plus 1, n minus 1 is greater than root n minus 1, n minus 1? Of course it is, because this expression on the left is greater than this one. So the inequality is true. And we can also rewrite the item on the right as root n minus 1 whole thing square, which will give us this. So therefore, our second ingredient, this is also true. If that's the case, n times n plus 2 plus this must be greater than this plus this, right? What's on the right hand side? It is 2n minus 1. So now we have shown that this blue denominator is actually bigger than this pink color denominator. This means that this expression now is greater than our previous answer, n squared plus 2n, using this logic here. Not very straightforward. That's why they only offer 2 marks to this extremely tough question. Question 10 is a two-parter. The first one wants you to do integration by parts and then ask you to find volume in part 2. The next one, which I haven't shown yet, it's a remain sum question. So let's focus on just part A. Find integrate x root x minus 1 dx using integration by parts. So one of these would be your u, the other would be your dv dx. It's a coin toss which one you chose. One of them will make the question harder and the other one will make the question simpler. So let's say, unfortunately, you have chosen this as your dv dx and this is your u. This will give you uv minus integrate v du. So let's take a look at how this will create some issue, because here no problem. uv is just an expression. It's the integration part that would create some problem. If this is your u, then your du dx would be half x minus 1 negative half. And your dv dx will be x squared over 2. And then here we want to integrate v du dx. V times du dx is actually more complicated than the actual question. So clearly this is not a good choice. When you find out that what we want to integrate here is more complicated than before, abort and just change up your u and your dv dx. So let's just do this properly. This will be your u, this will be your dv dx. So your u is x, your du dx would then be 1, and if your dv dx is x minus 1 to the power of half, your v would be x minus 1 to the power of 3 over 2 over 3 over 2, which is 2/3, x minus 1 to the power of 3 over 2. So your expression would just become uv minus integrate v du. 1. This is why we chose u as x, because it gives us something nice. dx. This will give us x minus 1 power 3 over 2. Pluck out the 2/3. Integrating what's remaining would give you x minus 1, 5 over 2 over 5 over 2 plus c, 2/3 x minus 1, 3 over 2, divided by 5 over 2 will give you 4 over 15, x minus 1 to the power of 5 over 2 plus c. That's our answer to the first part. Second part, the shape of metal sculpture formed by rotating region bounded by this scary looking curve, a square root within a square root, where a is a positive integer, lines x equals to 1 and y equals to a plus 30 square root. We're going to rotate it about the x-axis. So this curve, which we don't know what it looks like, is being rotated about the x-axis. So the correct formula to apply here would be to use the pi y square dx, because I'm rotating about the x-axis. So keep this in mind. We're going to use this. We have to now sort of draw it on our GC despite there being an a, which will create some trouble when we plot into the GC. It's okay, just put in any number you like, positive integer. So you can use like 1, 2, or 3, it doesn't matter. You should have a graph that looks like this. Here I've selected a to be equals to 2. It doesn't make a difference if you chose a lower a like 1. This value will just be slightly below, but the general shape still remains the same. Now you have to find out what the region is. X equals to 1 is clearly this particular line here. And y is equals to root a plus 30. Now here's the issue. You don't know where this horizontal line is. When y is equals to root a plus 30, can you tell that this means that this highlighted part is 30. So your job is simply solve for x root x minus 1 equals to 30. Usually, you'll give you an integer answer. If you really want to solve this, you can press GC to find this, but you can also solve this via mental sums because 30 is just 3 times 10. So if x is 10, root 10 minus 1, which is root 9, coincidentally gives you 30. So x is equals to 10. You can also solve this by squaring both sides, 900, x squared, x minus 1, and then solve this cubic equation using calculator. You end up with the same answer, x is equals to 10. This means that the horizontal line will cut the graph at 10. And the area that's bounded would be this red color area. Now, can you tell that if I were to rotate this red color area about the x-axis, it's actually this cylinder minus away the green color volume. So setup is cylinder minus away the green color area. It looks like a frustrum. You will get the red color volume, which is what they want. So this cylinder here is pi r square h, where the r is this length. This length would give us a plus 30 whole thing square. What is the height? The height is from 1 to x equals to 10. From 1 to 10 gives you 9. What about this one? This is square root of y squared dx like we chose before from 1 to 10. What is y squared? Y squared you can replace here. So when you square the square root, you're left without the square root. So it's simply this. Now if you were to look at this one, we actually done that in part 1 already. So let's go ahead and simplify this entire expression. So here you will get 9 pi times a plus 30 minus away integrate a dx from 1 to 10 minus away x minus 1 dx from 1 to 10 as well. So here what I did was I split this integration up into 2 parts and I applied the negative to both of them to give me this. This would give me 270 pi plus 9a pi minus, oh, I left out a pi, my bad. So both of these have pi's because the formula is pi integrate y squared dx. So here I'll get a pi on the outside as well. Then here, I know the answer to this part is really long. It's above this one. So I'm going to copy this. 2/3 x minus 1 power 3 over 2 minus 4 over 15 x minus 1 to the power 5 over 2. Evaluated from 1 to 10. Simplifying this further, here I'll have negative pi times 10a minus 1, which is minus away 9a pi in total. Here I will get pi. After simplifying, you get 576 over 5. And clean this up some more, cancel. I'll be left with 270 pi minus 576 over 5 pi, which gives us the answer 774 over 5 pi. And with that, we're done with part A, the integration by parts and then a volume question. Part 2, it's a Riemann sum question. Don't panic when you see this kind of question. Take note of rectangles. Find out the area of the rectangles one by one and you will be able to solve it. Let's take a look at the very first rectangle you see. What is the area of the first rectangle? Since after all they want to show the total rectangle of all the rectangles. So the first one, area of the first one is breadth multiply by the height. What is the height? Height, you can get it by subbing in 1 over n. Let me zoom in. You can sub in 1 over n into your equation to give you the y value. Turns out it's ln 1 plus 1 over n. So I'm going to take note. This will be ln 1 plus 1 over n. What about the second rectangle? Same breadth. Sub this time 2 over n in. I'll get 1 plus 2 over n. You get the idea, right? What about the last rectangle? Now you don't have to worry what number is the last rectangle. I tell you now it's n minus 1. You don't need to know it because they wouldn't ask you how many rectangles there are. So simply, you just write it as a last. What is the last one? Ln 1 plus what? What is the height of this rectangle? You're supposed to sub in the value right before 1 because 1 is at the end here. So the value right before 1 would be 1 minus 1 over n. What would that be? This would be n over n minus 1 over n. This gives us n minus 1 over n. So you already know that the last rectangle is the n minus 1th rectangle, since this number match this number here always. So if let's say like ask you what's A50, you'll be 1 over n ln 1 plus 50 over n. But this is not required. Next, we have to sum them all up. You notice we don't have to use summation here like we usually do. They ask you to sum it up and express it as this. There are no summation here. So when you sum them all up, it is simply you factorize out the 1 over n, and then you get a ln 1 plus 1 over n plus ln 1 plus 2 over n, all the way until ln 1 plus n minus 1 over n. And if we apply ln product rule, we will end up with this. Ln of 1 plus 1 over n multiplied by 1 plus 2 over n, multiply all the way until 1 plus n minus 1 over n. And I'm going to turn each and every one of these into fractions. For example, this one, I'll turn it into n over n, and I combine them. I should get n plus 1 over n here. Similarly here, I will get n plus 2 over n. And the final one, you will get 2n minus 1 over n. And then of course, if you multiply all of them together, you would get what they want you to show. N plus 1, n plus 2, all the way until 2n minus 1. And of course, the denominators are all multiplied together. How many n's are being multiplied together? There are n minus 1 of them. So this is why we will get this answer here. Now, what is the purpose of this expression? It is exactly what they want us to find in the next part. When we let the number of rectangles go to infinity, we can find the total area of all the rectangles by letting n go to infinity for this expression, because this is a. We will be able to find a. However, this is way beyond our scope of what we can do in math. We don't know what this will become. We don't know what this will become. It's a horrible nightmare to do. So this, our traditional approach, wouldn't work. You have to understand the idea that when n goes to infinity, what happens to the area? Instead of doing this mathematically, we have to know that it becomes the actual area under graph. This is the learning point of Riemann sums. The sum of area of rectangles underneath the curve when the number of rectangles goes to infinity is indeed the actual area underneath the curve done via integration. So this would actually be integrate from 0 to 1 of the curve, ln 1 plus x dx. So instead of n go to infinity for this horrible expression, we can simply solve it by integrating the curve from 0 to 1. This is still not easy because we have to add a 1 here and do it by parts, but at least it's not that bad. According to the LIATE rule, we should let logarithms be u. So here, u is your ln 1 plus x. Your du, dx would therefore be 1 over 1 plus x. And your v and your dv, dx will respectively be 1 and just x. So go ahead. uv minus integrate v du, x over 1 plus x dx from 0 to 1. This one, in order to do this one, we have to long divide it, which should give you, if you were to do this, you should give you 1 minus 1 over 1 plus x. Solving this will give you x minus ln 1 plus x. And if we were to clean this up, expand the brackets within, we will get x ln 1 plus x minus x plus ln 1 plus x. Factorize out the ln 1 plus x, we will get x plus 1 ln 1 plus x minus x from 0 to 1. And then now it's an easy case of summing in 1, which will give you 2 ln 2 minus 1, and then sum in 0. Ln 1 gives you 0, and 0 is here. So this is our final answer. The sum of rectangles as number of rectangles goes to infinity is equals to the actual integration, the area underneath the curve. Thank you for watching this video. See you in a bit.